So now we will start with the next tutorial, that is topology optimization with extrusion constraints. The extrusion constraints method allows you to perform an optimization problem with extrusion constraints to obtain a constant cross section along a given path, particularly in the case of parts manufactured through an extrusion process. By using extrusion manufacturing constraints in topology optimization, constant cross-section designs can be obtained for solid models regardless of initial mesh boundary conditions or loads. This tutorial shows the steps involved in defining topology optimization over a curved beam, simulating a rail over which a vehicle is moving. Both ends of the beam are supported. A point load is applied over the length of the rail in 7 independent load cases, simulating the movement of the vehicle. The rail should be manufactured through extrusion. The steps taken to define the topology design space, the extrusion manufacturing constraint, and the optimization parameters, response objective and constraints using HyperMesh will be shown. In this tutorial, we'll perform topology optimization on curved beam so that the extrusion rail will be stiffer and have less material. The optimization problem is stated as: my objective is to minimize the weighted compliances. My constraints are that the volume fraction should be less than 0.30, and the design variables are the density of each element in the design space. The DTPL, design variable for topology optimization card, is used for this optimization. The finite element mesh of the curved beam is shown in the following. As you can see here, the process covered in this tutorial are setting up extrusion constraint in HyperMesh, setting up optimization problem, and post-process the optimization results with extrusion constraint. So we'll open the HyperMesh. We'll just check the model file. As you can see, the model file is in .fem. So I will import this file. Click import. So you can see the representing arrows are very big, so we will decrease the size, say 50. And also the mesh lines, the meshing is in line mode, so we'll make it in a shaded mode. We can see the elements. My material, property, component, load collector and load step is predefined, as you can see here. So we'll directly proceed to the next step, that is to define the optimization parameters. So we will start up with setting up the extrusion constraints in HyperMesh. So first step is to create the topology design variables. So to create the topology design variables, we'll follow the same step, like go to analysis page. On analysis page, I will click on optimization. Select topology, first column, first row. Go to create radio button. Enter the design variable name as design solid. Select the property as new solid. Element types will be P solid. Click create. Then click return to exit, to go back to the optimization panel. Again click return to go back to the main menu. Then we will define the extrusion problem and extrusion path. So extrusion path we have to define. So we will go to tools page, numbers. On tools page, click on numbers panel. Click on the nodes and select by ID. So click on, from the drop box, make sure you have selected the nodes panel and click on the nodes on the yellow box and select by ID. Enter the node ID as 71559 and 70001. So it will select two nodes, as you can see. Click the display and say on. So it will keep the display on of these two node IDs so that we can define a path. Then click on return and go back to the analysis optimization topology panel. Now this time we will select extrusion radio button. On the fifth, you can see the extrusion radio button. Select the design variable. Switch none to no twist. So the extrusion constraint can be applied to domains characterized by non-twisted cross-section or twisted cross-section by using no twist or twist parameters respectively. Select the primary path and select node list by clicking on nodes by path. It is necessary to define a discrete extrusion parameter by path by entering a series of grids. The curve between these grids is then interpolated using parametric splines. The minimum amount of grid depends on complexity of the extrusion path. Only 2 grids are required for linear path, but it is recommended that at least 5 to 10 grids, that is the node path, be used for more complex curves. So select this first node, select another one, so it will select the path. In the same way, select any mid one till the last one. So in this way, a line of nodes starting from 71559 and end with 70001 should be highlighted, indicating the extrusion path. You do not have to select as many nodes to define the curve. This is an exercise to show that nodes by path options can be used. So click on update to update that selection. Then click return. Now the next step is to define the responses. So click on response radio button. Enter the response name as volume. Select the response type as volume fraction. From the region, select total. This will be as default and click on create. Then enter the response name as weighted compliances. Select the type as weighted compliances. Click on the load step and select all the predefined load steps. Click return and click create. So my design variable and responses is now being created, as you can see on the model browser. So the design variable and responses are defined. So click return. Then the next step is to define the constraint. So click on the constraint just below the response panel. Enter the constraint name, let's say constraint 1. Enter the response as volume. Check the box in front of lower bound and enter 0.3. Click create. So my constraint is defined. Then the next step is to define the objective. So my objective is to minimize the weighted compliances. Now we will save this file. And solve the model using OptiStruct. So click on analysis, OptiStruct, export option to all, run option to optimization, Memory option, keep it as much possible as you can, and click on OptiStruct. So this will start the solver window. You can see it has taken the amount of memory allotted for this run is 744. So it will automatically check how much memory is required. So as you can see, my optimization has converged and feasible design, that is all constraints are satisfied as message appears. So my analysis is done. So I will close the solver window and click on the results to view those results in HyperView. So the same thing which we have, which we did earlier also. So select the last iteration, contour, elemental densities, apply, ISO, element densities, apply, change it to 0.3 on the features and transparency. So you can see this much amount of material can be removed and withstand the minimum criteria of stress and displacement. So from inside also you can remove the material, as you can see a portion of that. So it has removed the material from inside. Also you can mask a portion to see this. Click revert so you can see. So if I go to ISO of these two things, so you can see unmask all, mask a portion of it, I'll mask a little portion of it and reverse. So you can see that. So in this way the material can be removed from inside as well as outside. So by this we have ended with the tutorial. Now we will move to the next tutorial. I'll close this. I'll click new. So now we will see how to perform frequency response optimization of a rectangular plate. So this tutorial demonstrates the capabilities of frequency response optimization using OptiStruct. Initially, an existing finite element model of a flat plate is retrieved and modal frequency response analysis is performed to derive the peak magnitude. A dynamic response optimization is then performed on the same plate to obtain a new design. The new design gives an optimized material layout with a minimized peak response. Post-processing tools will be used in HyperView to visualize isoplots, magnitude and phase of the complex displacement result. My objective of the optimization is to minimize the volume. My constraint is the maximum FRF displacement should be greater than 600 mm. My design variables are the density of each element in the design space. The process which we are going to cover in this tutorial are setting up a modal frequency response analysis in HyperMesh, post-process FRF results, set up topology optimization and post-process the topologic results. So we will check the file type first. So my file type is FEM, so I will import that in HyperWorks. So I will go to import, select the file type as OptiStruct and click on import. So I import the model. My material, property, component is defined, but in this model the load collector and load step is not defined. So I have to define that load collector and load step. So you can see the mesh in the line mode. So you click on shaded geometry to view the mesh, as you can see here. So We'll start off with setting up a module frequency response analysis in HyperMesh. So the first step is to create the SPC and unit load collectors. So in this session, the model is constrained at one edge. A unit vector load will be applied acting upwards in the positive Z direction at a point on a free edge corner of a plate. We first need to create two loads collector, SPCs and unit load. So we'll first create a two load collectors. Go to load collector, click on SPCS, define a color with no card image, click on create, and unit load, define another color even with no card image and click create. So on the model browser you can see my SPC and unit load, two load collectors are defined. Now we will create the constraint. So click return to go back to the main menu and create the constraints. So to create the constraints, go to analysis. On analysis, click on constraints. Before that, we will select the tools number and generate the numbers by ID, same as we did earlier. So these are the numbers. So I'll go to analysis, constraints. So select the node IDs 1 and 2 and constraints all the degrees of freedom, but we have to make the SPC as the current. So I will right click on that and make the SPC as make current. So that will be bold. Bold is the current component or load collector. Click create. So this is created. Then click on the node ID 4. Check the box in front of DOF3 and click on create. Then click return to go back to the main menu and make the unit load as the current. Just right click on it and click on make current. Then again we'll go to analysis page, constraints. This time for the load type we will select D area to define the unit load. So we'll select the node number as the third node number. Check the box in front of DOF3 and enter the value as 20 and click on create. So it has defined that, as you can see. So I'll make it in this way. So 1, 2, 3, 4. So tools, numbers of. So I have defined these. Now I will create a frequency range table. So we'll again create one more load collector as table T1. Set a color to it, different from the earlier one. This time we will give a card image as table D1. Here it is, table D1 card image, and click on create edit to enter these values for the table D1 card image. We will enter the table number as 2. In the X1 value we will enter 0, Y1 1, X2 1000 and Y2 1. So this gives a frequency range of 0 to 1000 with a constant load over this range. Then we will click return to go back to the main menu, or sorry, load collector menu. Then we will create a frequency dependent dynamic load. So again, be here on the load collector icon Enter the load collector name as rload2. You can enter any name as per your choice. Then select the card image as rload2. Define a different color. Click on create edit. Then select XID and select unit load. Then select TB and select table D1. Select the type as load. In this way, we have defined the frequency dependent dynamic load. Click return to go back to the load collector menu. Then we will create a set of frequencies to be used in response solution. So enter the load collector name as FREQ5. Card image as FREQI. Give a different color. Click on create edit. Check the box in front of frequency 5. Scroll it down. Keep the number of frequency 5 as 1 and frequency 5 max number frequency change it to 3. In F11 enter the value as 1. In F2 enter the value as 1000. In FR00 enter 1. 0,1 enter 0.8. 0,2 enter 0.2. So this defines a set of frequency for modal method of frequency response analysis by specifying a range of frequency and a fraction of natural frequency with that range. So we have defined that. So click return to go back to the load collector menu. Then we will create a load collector EIGRL to use as the modal method. So I will enter the value as name as EIGRL. Card image as EIGRL. Define a different color. Click on create edit. Enter the ND as 17. So for 17 modes we require. So this specifies the eigenvalue extraction for first 17 frequencies using Langham's method. So we will now create a OptiStruct load step, which is also referred as subcase. So I'll go to analysis page, load step, enter the name as subcase 1, choose the type as frequency response model, check the box in front of SPC and select SPCS, check the box in method structure, select EIGRL, check the box in front of dload, select rload2, check the box in front of FREQ, that is frequency, select FREQ5 and click create. So an OptiStruct subcase has been created with reference the constraint in the load collector SPC, the unit load in the load collector rload2 and a set of frequency defined in the load collector frequency 5 and modal method defined in the load collector EIGRL. It is recommended to do a modal analysis before an FRF simulation. Here this step is suppressed to focus a frequency response analysis, that is FRF. Setup. Then click on edit. Scroll down and check the box in front of RESVEC. So check the box in front of RESVEC. Set the type as apply load, app load and option as yes. Click return. Now create a set of nodes for the output of the results. So I'll go to click return again to go back to the main menu. Go to analysis page, entity sets. So we will create a set of nodes to get the desired output faster. enter the name as set A. Select the card image as set grid. Select the type as non-order. Click entity and choose nodes. Select the node ID 3. So we want the results output on this particular node. So displacement, everything will be on that particular node. So all the other component will not take part in the output. It will take part in the analysis, but not the output result. So that my analysis will solve much faster. Click create. So with FRF simulation, the amount of data generated can easily create a big result file. It is a good practice to work with a set where the user can specify only the point of interest. This will reduce CPU time and the amount of data to be saved. It creates a bigger file, the FRF simulation. So we will create a set of outputs and include damping for frequency response analysis. So we'll click return to go back to the main menu. Then on the analysis page, we will select control cards. We will go to global output request, click on next, global output request. Check the box in front of displacement. Click on form and select phase. Click on options and select SID and select set A as the SID. Click return to go back to the control card panel. Select format from the menu. Go to preview, format. In the number of formats, enter 2. On the first, select Opti, and select second, keep it as, or on the second select Opti, keep the first one as S3D. Click return to go back to the control card menu. Then go to param card, scroll it down till G. So enter the GV1 value as 0.05. So this specifies that the system will have a constant damping coefficient equal to 2.5 of the critical damping ratio. So then click on return to go back to the control card panel. Click output. Enter the output as HG reference, HG frequency. Set the frequency to the last. So we want only the last frequency in the output. Click return. Again click return to go back to the main menu. Now we will save this file. And perform an OptiStruct analysis. So go to analysis, OptiStruct, export option to all, run option to analysis, memory option you can increase to 1 GB, and click on OptiStruct. So this will start the solver. So now as you can see, my analysis is completed. So I will click on results to view the results in HyperView as well as in HyperGraph, because we will see the peak values. So instead of HyperView results of displacement and stress, we will open the session and we will open the frequency MVM session to view the displacement of the peak values. So first, make sure it is selected the subcase 1, displacement of grid point 3, only particularly on that point what will be the displacement grid that this is showing. The top graph, this top graph shows the phase angle versus frequency, and the bottom graph shows the displacement response versus frequency. Now click on define curves button, this button, and delete the X trans and Y trans curves. X trans and Y trans curves. So the excitation is applied on Z direction, then the main effect will be detected on this direction only. So as we have excited that particular node in Z direction, so we will see the result in Z direction only. Then click on curve attributes button, this curve attributes. Change the line attribute to continuous. Click on symbol attribute and select the square symbol. So it will show you the peak values. Then click on axis button and change it to vertical. Click on the scale, tips and ticks magnitude. Enter the minimum value as 5 and maximum as 2 lakh. Then click on scale and ticks phase. Change the ticks per axis value to 7. Click on horizontal X and change the minimum value to 5 and maximum to 1000. Change it here also. Then click on coordinate info. And you can see the curves values. So this is the maximum value, as you can see the maximum peak. So it gives the y-axis values, y-axis phase values, x displacement, y phase and y magnitude. So x is the frequency, y phase values, and y magnitude is the displacement value. So in this way you can view the results of frequency response in hypergraph. So I'll close this and I'll go to the next step by creating a design variable for topology optimization. So with the base model, we'll move to the next of defining the topology optimization for the frequency response analysis. So I'll click return. On the same model, we'll start with the optimization. So analysis, OptiStruct. So we will go to topology, enter the design variable name as plate, select the property, enter the type as P shell with a base thickness of 0.15. So it can create a bit pattern. So it will show where to create a bit pattern to decrease the frequency or to achieve that frequency. Click create. Go to parameters, minimum member to 2, maximum member to 6. Click on update. So a topology design space define a plate space definition. Plate has been created. All elements organized into the design component collector are now included in the design space. The thickness of these shells can vary between 0.15, the base thickness defined above, and the maximum thickness defined by the T, that is the thickness of in the property field. The object of this expression is to determine where to locate ribs in the designable region. Therefore, zero base thickness is defined, non-zero base thickness is defined, which is the original thickness of the shell. The maximum thickness is defined by T field on the P shell card should be allowable depth of the ribs. Currently, the T field P shell is still on 0.15, as you can see. I will click on the property collector, update, select the property, click on update edit. It's still on 0.15, so I will change it to 1. So this is the allowable depth I am giving to create the ribs pattern. So this needs to be changed so that a range of the thickness we can get it. So now click return to go back to the optimization topology optimization panel. Now the next step is to create the responses. So I will click on the responses panel. Enter the response name as FRF displacement. Enter the response type as FRF displacement. We have to make sure that the component switch is selected to magnitude. And the function switch is set to all frequencies. Click on the yellow box by ID, node number 3. Select degree of freedom 3 and click create. A response FRF displacement is defined for maximum magnitude of DOF3. Then create another response as volume. Select the response type as volume. Make all the things as by default and click create. So my two responses has been defined, as you can see. My design variable is defined, my optimization responses is defined. So the next step is to define the constraints. So I will click return, go back to the T constraint panel, enter the constraint name as say constraint. My response is FRF displacement. The upper bound value for the FRF displacement is 600 mm and the load step is subcase 1. Click create. So my constraint is defined. Then my objective is to minimize the response. So my objective is also defined. Now I will save this file in the same folder but just changing the name. Go to analysis, OptiStruct, export option to all, run option to optimization. Memory I will keep as 1 GB as it is, and click on OptiStruct. So this will start the solver window. So now as we can see, the optimization has converged and feasible design via all constraints are satisfied is achieved. So I will click on the results to view the beat patterns from this optimization process. So where exactly the beat patterns are going to come, that we will see. So in the same way, we will select the last iteration as the 71th. Element densities apply, and we will not go ISO because we are not going to remove the material exactly, but we are going to see the areas where we can create a beat structure to get a maximum displacement because of the dynamic frequency to be somewhere around 600. So these are the areas where we can create a beat patterns and get an appropriate frequency. So in this way, the OptiStruct helps us to get a beat patterns also to increase or decrease the displacement because of the dynamic frequencies. So by this, we have ended with the next tutorial. So I'll click on new, and we'll move to the last tutorial of this training session, also of day 6. So the last tutorial is, we'll see how to perform topology optimization on an excavator arm model. This tutorial demonstrates how to set up an optimization problem of an MBD system using the equivalent static load method, ESL. The model is set up in HyperMesh and the topology optimization job is run with OptiStruct. The objective of the optimization is to maximize the stiffness of the lower arm of an excavator model while keeping the mass to less than an allowable value. The model units are kg, Newton, meters and seconds. The optimization problem for this tutorial is stated as, my objective is to minimize the maximum compliances in an ESL load step. My constraint is the upper bound on the volume fraction. My design variable is element densities of element in the lower arm flexible body component. In this tutorial, we will see review an MBD transient analysis, change one of the rigid body to a flexible body, set up and run topology optimization on MBD system using the equivalent static load ESL method, post-process the optimization results in Hyperview. So we'll start up with checking up the file type. So my file type is HM. So I will open it, the HM file. So this is my mesh model of an excavator arm with the joints and everything is defined, as you can see. So my material properties, components, load collectors, load step, everything is predefined. So we will just solve this model and see the results of the analysis. So we'll save this model on desktop. See. So we'll save it. Go to analysis, OptiStruct, export option to all, run option to analysis. Memory option will keep it as same, 4 GB, it's good. You can also keep by default, that is not an issue, but it will solve on the by default memory also. But increasing the memory will decrease the solver time. So it's always good to put a higher range of memory. So you can see it started with the analysis. So here you can see the process is still going on. You can check continuously if you click by date, so you can see continuously the process is going up and down. So once it will generate all the files, we will see the results then. I think the earlier session the video is not visual, so I'll quickly say that this is the base model I have used for the excavator arm, and I have just opened this model in HyperMesh, and without doing anything, just checking it, I have just solved it. So I haven't done anything. So if you are not able to view this, so still you can get it. Or I'll go a little back. If you are not able to view the results of optimized beat patterns, I will open that also. So I'll go to open model and just click on OptiStruct or open the HyperView directly. So I'm not sure whether you are able to view this early also, but if you don't, I'll show you again. So we will open the file, say apply. So in the same way, iteration number last 71, contour, apply. So these are the beat patterns. So if you are not able to see earlier, you can see it right now. I'll close this. Also click on new. So I've just solved it. As you can see, I've just solved that model. So I will see the results of MBD analysis first. So I'll click on play. So you can see it is processing the steps. So this is the MBD results. If you lower down the speed, you can see. So this is my excavator arm with MBD predefined model. So I will close it and move to the optimization process. So my first step will change the rigid body into flexible body. In this step, we are going to define topology optimization on the body lower arm. I will show you. Isolate only, so you can see this is the lower arm where we are going to do the optimization on this particular body. Its original models are rigid body and need to be converted to a flexible body for the optimization. So we will just convert the rigid bodies into flexible bodies for the optimization. So we'll click return. On analysis page, we will click on bodies, select update, click on the body type and select lower arm. We'll click on review. So the lower arm component is highlighted. Body type is our body is shown for the type, indicating that lower arm is modeled as rigid body. We will update this body to flexible body type and also define topology optimization on this body. So we will select the type as PF body, that is flexible body. Enter 20 under N modes to increase the number of modes included in CMS method to 20. Click update and click return. So we have converted this into flexible body. Now we will define the topology design variable. So analysis, OptiStruct, topology. Go to create radio button. Enter the design variable name, let's suppose arm topology. Click on the property and select lower arm property. Enter the type as P solid and click on create. Then select parameters. Click on lower arm. Toggle the minimum member off to minimum dimension and enter the minimum dimension value to 0.05 and click update. So minimum member size controls of 0.05 meter has been applied on this topology optimization problem. Now we will define the responses. I'll click return to exit, go back to the optimization panel. Click on responses. Enter the response type as volume fraction. Select the type as volume fraction. Click the entity by total. And property we will select lower arm. Select and create. Then again we will create one more response as compliances. Enter the type as compliances. Make it to total and click create. So my responses is defined. I will click return to go back to the optimization panel. We will define the objective reference. So click on objective reference. Enter the objective reference name as max compliances. Positive reference, check the box and check negative reference. Click the response type as compliances. Set the load step section option to total. To make sure the design objective reference includes compliances from all the load steps that are included by ESL method. Then we'll click on create and return. Then we will define the objective function. So click on objective and define mean max and define the objective reference and click create. So my objective is to minimize the maximum value. So as on the PPT you can see, my objective is to minimize the maximum compliances. So I have selected the mean max objective. Now click return to go back to the optimization panel. Now we will define the constraints. Enter the constraint name as volume constraint. Check the box in front of lower bound and enter the value as 0.5. Select the response as volume fraction and click create. So a constraint is defined on the response volume fraction. The constraint will force the volume fraction used in the design space to be less than 0.5. So click return. Save this file. I'll save in the same folder by changing a name to 1. We'll go to analysis, OptiStruct, export option to all, run option to this time optimization. Memory I will keep as 4 GB and click on OptiStruct. So this will start the optimization process. So my analysis is completed. This is my flex body analysis for the mode. So this is the rotation values, the strain values, the stress values, and the displacement values. So these are the results which you can see. So in this way, I have ended with the online training session day 6, topology optimization part 2, which is the last part of this day 6. Thank you very much for attending this session. If you like us to improve the online training session, please help us by sharing your valuable comments at support@india.altera.com. Also, if you find anything interesting or informative in this training series or in any of the training videos, then also to motivate us, please drop us your valuable comments on edu-support@india.altera.com. Thank you very much. Have a great day.